Okay, so today let's go ahead and return to general gravity, meaning Newtonian gravity in the general sense, and we'll be looking at deriving something called Kepler's equation. Now, Kepler has his name on a lot of different things, so I'm not just talking about Kepler's 3 laws. We've already seen a couple of these, like the fact that conic sections come out of the application of Newton's laws to universal gravitation, and the second law, of course, being that areal velocity being constant. We'll get to the third law actually very soon. But this one is actually Kepler's equation. And it's an equation that was studied quite a bit throughout, say, 17th century, well, honestly, up until modern times. And it's one of those equations that really gave a lot of smart people a lot of trouble, even though it looks relatively straightforward. So here's the basic idea. I'm going to do a little bit of a quick review of where this comes from. So imagine again that we have a central potential. It's a 1 over r potential. It's Newtonian gravity. And we're going to write down the total mechanical energy of some particle moving under the influence of that gravitational force. So its total mechanical energy we'll call capital E. That's just sort of how much total energy it has. Could be positive, could be negative, it depends. And we know that that's going to be written as some sort of radial kinetic energy. So the r dot here is the rate of change of the distance between the two objects, as well as this angular piece, which is really often lumped in with the actual potential to form the effective potential energy. So this angular piece depends on the angular momentum of the particle. That's that capital L. And as a reminder about the notation here, really, I'm imagining 2 objects, say mass 1 and mass 2, that are separated by some distance r. So that's what the r in this stands for. It's the relative separation between the 2 masses. I'm not necessarily assuming that one of them is stationary and the other one's doing orbits about it. They could be completely general. R here does represent the relative distance between them. And mu, which is shown here and here, that's the reduced mass of the system, which, remember, is the product of the masses divided by their sum. It's the effective mass of the whole system. We reduced the 2-body problem to an effective 1-body problem in a previous video. And then, of course, the actual potential energy, I'm assuming right now that it's an attractive potential energy, hence the minus sign. It's a 1 over r potential. That's why we have a 1 over r squared force. And this kappa really is sort of a generic 1 over r squared force. In our particular case, we're usually assuming that kappa is something like big G times the product of the 2 masses. But this can work also for things like Coulomb potential in electrostatics. That's totally fine also. And what we did in a previous video was we basically solved for this r dot. Okay, you got to move some stuff around, take square roots. We took the positive root. And then we're going to separate variables. Remember, this is dr dt. So if we do that, we end up with this nice separated form where t can be written on its own. We integrated that. And then we've got a whole bunch of stuff that depends on r. And unfortunately, it's really messy as is. There'll be some initial condition, whatever r naught is, will sort of set the overall size, or at least the overall starting point of our trajectory. And then we need to do this integral. Now, we actually don't want to do this integral. This is a kind of messy integral. We're going to make a slight change of variables and look at some of the geometry of this problem to make things a little easier on us. So the first thing I want to do is notice that as it is, it's kind of a mess. Let's go ahead and notice that I have a constant. I have a 1 over r squared and a 1 over r, all under this square root that's all in the denominator. It would be pretty nice if I could make this look a little bit less of a compound fraction. So I'm going to go ahead, I'm going to pull out this 1 over r squared, which is the largest power, if you want, in the denominator, out of everything, and see what that does to my equation. So notice that if I pull out a 1 over r squared from this term, I'll be left with a constant. Pulling a 1 over r squared out of this term will leave me with an r times this kappa, and then I'll have an e times r squared here. That 1 over r squared will come out of the root as a 1 over r, and it'll flip up to the top. So I'm expecting something that looks like this. Okay, the next thing I'm going to do is I'm going to do a couple more bits of simplification. So first off, let's go ahead and pull this kappa out of every single term. And that will leave just an r here. And then we'll be left with a couple convenient forms. So if we do that, okay, I know that these are kind of messy integrals, so we're just going step by step here. All right, so here's a slightly rewritten form. At least it doesn't have any compound fractions in it. Now, at this point, I actually want to turn specifically to bounded motion, meaning I want to look for the case where e is less than 0. And in those cases, we know that our orbits, being conic sections, are going to have to be ellipses, maybe a degenerate sort of ellipse or a circle, a special case, but we know that we have to have ellipses. Okay, so now we want to find out what this total energy is, and we're going to write it in terms of the semi-major axis of the elliptical orbit. And remember that what we're thinking of here is we have an ellipse in polar coordinates. One of the foci of that ellipse will be the pole, kind of imagining something like this. R is measuring out to these locations on the ellipse. And then we know that from one apside to the other, and that is the terminology we use here, these 2 points of furthest and closest approach to the pole are called the apsides. We have an apoapsis, that's the farthest away point, and we have a periapsis, which is the closest point. By the way, those names change depending on what the central object is that we're orbiting. For example, if this is a satellite around Earth, we'd call this the apogee and the perigee. If this is the Sun, we call this the aphelion and the perihelion. If it's Saturn, we call this I think it's apochrone and perichrone or something like that. So unfortunately, there's a lot of terms. They all mean the same thing. And we know from our general knowledge of ellipses that this distance all the way across is often written as 2a, where a is the semi-major axis. So this is the major axis. We would also have a minor axis, and we typically label these as a. That's this distance here. Maybe I'll put that in a different color here. So a is this semi-major axis. And then for later, if we need it, we also typically have this distance, which is b, the semi-minor axis. All of that's not related directly to what the focal distance is from this point to other places on the trajectory, but we want to write down the total energy of this elliptical orbit in terms of its semi-major axis. Now, one quick way that we can do that is we can turn back to this original equation, recognize that at, say, one of these 2 apsides, that r dot is 0. It's not moving out or in if we're at the closest or furthest away point. And so if I plug in what the values of r are at those 2 locations, we can get 2 equations that relate L, kappa, E, etc. all together in terms of this total distance, which is 2a. And as we've done in a previous video, we end up with this nice relation that the total energy of an elliptical orbit is minus this kappa, which again, we're thinking of like GMM, something like that, divided by 2a. So that's kind of nice. And it is a negative number because, of course, this is a bound state. So now what I want to do is I want to turn back to this integral, and I want to introduce a little bit of notation that'll simplify it. For one, we're going to plug in what this E is. So my R can be written in something depending on A, the semi-major axis, which is related to how large the orbit is. I also want to look at this thing here, L squared over 2 mu k. There's a commonly used notation, which is P, which is supposed to be L squared over mu k, kappa. This distance is called the semilattice rectum. Always fun to include a bit of Latin here. And the semilattice rectum is basically this distance here. Well, it's actually half of that. So this P is the it's half, lattice rectum. The lattice rectum is a segment that is drawn through the focus of a conic section perpendicular to its axis of symmetry. So This particular segment would be the full lattice rectum, and then this P is the semi-lattice rectum. And it turns out this is this value, L squared over mu kappa. You can check that that gives you the right units of distance. And we see that that shows up here, except with a little extra 2. So it might be nice to rewrite things in terms of this P. We also want to remember something that we derived earlier, which is what the eccentricity of the orbit is. And as a reminder, do I have room? I have room. Okay, if I want to write down the eccentricity. That's actually going to be square root of 1 plus twice the energy times L squared over mu kappa squared. We could go rewrite this, for example, in terms of P and A if we want. The point is, this combo is going to be pretty useful for us when we're writing everything down. So let's go ahead, let's clear this up a little bit. I'm going to rewrite my expression for this T in terms of these new parameters like P, epsilon, and A. Okay, so a little clustering of some reminders here. The total energy of an elliptical orbit, which is negative, depends on the semi-major axis. The semi-lattice rectum can be written in terms of the orbital angular momentum, and the eccentricity involves both the energy and the orbital angular momentum. There's a lot of ways we could rewrite all of these in terms of each other. I'm going to go ahead and use these two relations with the energy to write down a nice geometric factor, which is that this semi-lattice rectum P can be written directly in terms of the semi-major axis A and the eccentricity directly. Using that in our previous expression for the integral for T, we can write down, it's a little cleaner, I guess. It's still a little messy, but we do end up with something that's got a nice quadratic term here, our R, and then this constant term. I could have written it as P over 2, but we'll go ahead and use this new relation. Everything is in terms of A now. And, well, at this point, we could try to actually do that integral. However, it's not actually the cleanest or most useful form. There's a very commonly used substitution at this point, which lets us transform this into something that's a lot more manageable. And that substitution is, let's introduce a new variable called psi via this function. So I'm going to replace my R variable, which is my radial variable, with the semi-major axis times 1 minus the eccentricity times the cosine of psi. Now, the reason why this is convenient is, first of all, it should kind of remind you a little bit of the orbital equation. And as a reminder, maybe I'll put that in blue here. We know that R is actually P over 1 plus epsilon cosine of phi. And this came directly from solving Kepler's equation. So this 1 plus an eccentricity times a cosine does show up quite often in a lot of these problems. This is, however, not that. This is a conic section. What is this? Why are we doing this? What does this angle psi even represent? So the angle psi has a name. It's called the eccentric anomaly. And although it doesn't really have a nice physical interpretation, it is an angle, and it does actually range over the same amount of angle as phi. Remember, phi was our polar angle here. If I'm imagining some general location, say, I don't know, here, then this angle here would be phi, and this distance here would be r. So that's our usual expression. And you can see that everything recovers. Like, for example, when phi equals pi over 2, cosine of pi over 2 is 0, I get r equals p. So that's kind of why the semi-lattice rectum shows up so naturally here. We can also see that when phi is equal to 0, I'm at my periapsis, my closest approach here, and cosine of 0, of course, is 1. So I'm expecting this distance to be p over 1 plus epsilon, and then sure enough, you can plug in cosine of pi, and you'll get that this distance is p over 1 minus epsilon. So all the different orbital distances and parameters come pretty naturally from the orbit equation that we've already defined. So what is this? Well, the actual shape of this curve is a cardioid. If I were trying to graph it on the same polar plane with psi being kind of an angular variable just like this, the shape of that, and I'll do it I don't really want to mess things up by making too many pictures here, but the general shape will look something like a heart. I'm not doing a very good job here, but something like a heart. I'll make it as light as I can. A cardioid shape, and if you've taken some classes with polar coordinates, you might know that that's the equation of a cardioid. One important thing about this shape, though, is it has the same apsides. So notice that when psi now is equal to 0, I have cosine of 0, which is 1, and I have a times 1 minus epsilon. Now, that doesn't look like what we would have down here when phi equals 0, but remember, p and a are related by a 1 minus epsilon squared, and so you can see that p over 1 plus epsilon is the same as a times 1 minus epsilon. Just factor this as a difference of squares, and you can see that. The same thing happens at the apoapsis. So, okay, that's kind of nice. This is not the trajectory of the particle. I'm not saying that these things are moving on cardioids. That'd be unusual. But this is a very nice mathematical substitution. It has a lot of the same analytical properties as the actual orbital equation, and it's going to let us do this integral really easily. So let's see what happens when we make that substitution. First off, let's see what we can factor out of all this. Everything's written in terms of this a. So the a here, the a squared over a here, and the a there can all come out. That's nice. There's going to be an a up top for both of those because I'm going to have my chain rule. So I'll have an a squared divided by root a. Okay, in other words, I can put all of that under a single square root. With an a cubed. Okay, yeah, that makes sense. A squared over square root of a is a to the 3/2, which I'll put under the root. My bounds of integration are now going to go from, well, R0 up until this point has just sort of been a starting point. But if I'm going to be using this form of the orbital equation and trying to match it onto this eccentric anomaly version, I really have already chosen R0. It's the R when my angle is 0, which we already know is this periapsis value. Now, I could plug in what that is explicitly. We already kind of said it's going to be p over 1 plus epsilon. But I'm changing variables to this psi. And I know that that psi variable starts at 0. That's kind of what I mean by R0. That's this value here. And it's going to integrate up to psi. Now I just have to do a little bit of calculus stuff. I already pulled all the a's out. So I'm going to write this as 1 minus epsilon cosine psi. And then I've got a dr, which by the chain rule, again, the a is already there. I'm going to have a derivative of negative epsilon cosine, but derivative of cosine is negative sine, so the negative signs will cancel out, and I'll have an epsilon sine psi d psi in the numerator. Okay, it doesn't look like we're making this much nicer, but let's check the denominator now. A big old square root. I'm going to have a bunch of terms. The a's have already been pulled out, as a reminder. So we've got, what? 1 minus epsilon cosine psi, that's my r term, minus 1/2, again, the a's are all gone, times this thing squared, and then minus 1/2, again, the a has been pulled out, 1 minus epsilon squared. Okay, getting towards the end there, but let's see how this works out. We're hoping that there's going to be some nice simplifications, and indeed, there will be. I'm going to leave the numerator as is. But I'm going to try to expand out the denominator. Okay, I've got a 1 from this term. I have a minus 1/2 times a 1 squared from this term, and minus another 1/2 times a 1 from this term. So 1 minus 1/2 is 0. So there's no constant term here. I have a minus epsilon cosine psi. I'll go ahead and write that. When I expand this out, I'm going to end up with a cross term of minus 2 epsilon cosine, but then times minus 1/2. So that's going to be plus epsilon cosine. Oh, that's going to be nice. This squared term I'll have a minus sign, and then when we square it, I'll have a positive. So minus, because there's a minus sign on the outside, 1/2 epsilon squared cosine squared psi. And then my very last term will be a minus minus, which will be a plus epsilon squared. Okay, we can now see a little bit of simplification. These guys cancel out. There's an epsilon squared in both of these terms, which can cancel this epsilon in the numerator. And then what am I left with? 1 minus, oops, I forgot a 1/2 there, didn't I? Yes. Should have been a 1/2. Okay. And then what I'm left with here is a 1/2 minus 1/2 cosine squared. Well, 1 minus cosine squared is sine squared. It's under a square root. I am only needing to worry about positive values here. If you want to be very careful, you can take this over any range and the bounds will change appropriately. But the square root of sine squared is going to give me a sine. The only thing that's kind of left over is a 1/2. A square root of a 1/2. And when we simplify it all with the square root of 1/2 that shows up outside, I end up with something pretty nice. Everything else has canceled away, including this sign of psi upstairs and the cosine plus 1, cosine squared, negative cosine squared plus 1 downstairs. And we're just left with 1 minus epsilon cosine psi d psi. Oh, well, that's real nice. That's something I can very easily integrate. So when I do this integral, I'll get psi for this one, and then the antiderivative of cosine is sine. Notice that I am going to still plug in psi equals psi, and psi equals 0, sine of 0 is 0. So I get a very nice equation. Let's bring that up to the top and finish that off. Okay, so there it is. We can do one last little step. First of all, let's recognize that after one full time around, phi and psi will both have advanced by 2 pi. They actually do have the same range of angle. So if I plug in psi equals 2 pi compared to psi equals 0, which was my starting value, I should get one full revolution. In other words, the period, the total time to go through one full elliptical cycle, is going to be this times psi plugged in as 2 pi. But sine of 2 pi is 0, so I just get 2 pi times this square root. We have just recovered Kepler's third law that tells us that the period of an elliptical orbit is proportional to the 3/2 power of its size, or its semi-major axis. If we wanted to be a little more explicit, we can go ahead and plug in what the mu and the kappa are, recalling their definitions. And we'll go ahead and write that. So mu is going to be a product over a sum. Kappa has a product in it. So this will be a cubed over big G times the sum of the two masses in the case of gravity. So this is Kepler's third law. That's nice. That kind of came for free. We didn't have to do anything more. We also can use this to define a period of revolution. So let's define omega then to be 2 pi over this. And if we do that, we end up with a very nice little equation. And this equation right here, which I'll box in red, this equation is called Kepler's equation. It tells us what psi as a function of t is, recalling that r as a function of psi was also written down. So in principle, if I could use this equation to solve for psi, I could plug it in here and I would get r of t. Now, there's a bit of a problem. This is a very famously transcendental equation. I've got psi minus a trigonometric function of psi. So trying to invert this is pretty much impossible in terms of elementary functions. And that means that for centuries, people were trying to find some way of solving this psi in terms of t to then plug in and get an equation for the orbit directly. Now, we could have just gone right back to the original integral. It's erased now, but the original integral that we started with, and leave it in terms of that integral. That integral is also going to be special functions. We can't really get around that. But using this version of Kepler's equation, we're able to make some pretty good analytical headway. It can be, of course, approximated numerically, etc., to try to find approximate solutions numerically. As a final step here, we can also relate psi directly to phi. So the eccentric anomaly, psi, can be directly mapped onto the actual polar angle phi by remembering the orbital equation. So setting these two equal to each other, doing a little bit of cross-multiplying, factoring, and some trig identities, we can get a nice little relation between the tangent of at least the half angle phi this one's plus, and the half tangent of psi. So at least we have kind of a nice expression that relates the two angular variables in our problem. Okay, so I think that that's a pretty good summary of how to analyze elliptical orbits. We're introducing a few terms or notations that are going to be pretty common for elliptical orbits: the semi-lattice rectum, the semi-major axis, its eccentricity, of course, the total energy. And using that to essentially evaluate that nasty integral for r of t, but in a not completely analytical way that leads to our nice little new guy, the Kepler equation. And if we combine that with the orbital equation, maybe we have a little bit more to deal with. QED.